Hello there guys, welcome back to today the feedback lessons. Make sure that you perform your work properly, yeah? Now let's take a look at the marks, and the marks will tell you how many stuff you need. Okay, any calculation that you got wrong, you make sure that you know how to get it right. Okay, alright, now first question here is we have momentum. Now we know that the total momentum in this case is these guys. So we have two skaters are traveling together, so two of them are together, okay, and in a straight line the velocity is this one here. Now let's take a look. So we've got two skates. So let's take a look. So one and then two. Okay, they're going together. The velocity is 3.5 meters per second. Okay, so that they are together. Tell us that the total momentum is this much. Work out the mass of the person. Now we know that the one total momentum. So total momentum. So that's P is equal to V. Now since we're looking for the total, so therefore this here will be total momentum, and mass also will be the total. So therefore it's going to be 371 is equal to total mass will be the mass of the person, so mass of the man plus the mass of the woman multiplied by the velocity. Okay. Now the mass of the man is, we know, is 64.5 plus the mass of the woman, which we don't know, multiplied by 3.5. So therefore we have 3 divided by this equal to 64.5 plus women. So this will give us, so if we do this on calculator, this would be 6. And therefore we need to work out what is the mass of the man. So we know that this is equal to plus mass of the woman, so therefore 106 take away this equal to mass of the woman, so therefore this take away our answer. This will be, and this is our answer there. Okay, now using the fact that the total momentum is equal to the total velocity, the total mass times the velocity. Now these guys are together. It tells us that they are traveling together at a straight line. The velocity is this much. Okay. Now question here, we're looking for the kinetic energy. That's one of the equations which you guys need to remember. So kinetic energy is equal to half mv squared. Now half mv, we're looking for the man, so it's going to be times 64.5 times the velocity is squared. Okay, don't forget to square the velocity, and if you do this on your calculator, you are going to get your nice answer there. Okay, joules. Okay, now for this question here, you need to remember the equation for kinetic energy, and this will be able to do. This will help you do the rest. Okay. Question 1 was okay. Now let's move to this one here. Now this is a two-part equation. So let's take what we got. Now we need to work out how far this is. So we need to work out this distance there. We don't know this distance. Okay. What we do know is we do know acceleration. We do know the velocity at p. So this is our initial velocity, and we do know the velocity when it reaches q. This is our final velocity. Okay. Good. Now work out the distance. So luckily, one of the equations given to you was v squared is equal to u squared plus 2as. Now a is the distance in case, that's what we are looking for. So v take away u divided by 2a, let's go to our s. Now v we know, okay, minus u we know, by 2 times 3, and this will give us our answer straight away. Okay, and this is how long it is. So therefore the distance between p and q is equal to 68 meters. Now the question here, how long does it take? Okay, how long does it take to travel this much? Now the thing is, we've got two velocities here. So we can't use, so we've got two velocities here. We have distance equal to speed times time. So we can't use this because we've got two velocities. Okay, so what we're going to do is we are going to be looking for the time taken. I'm going to use this equation here because what we have is we have A, we have U, we have V, and we're looking for T. So acceleration is a change of velocity over time. Now, looking for time, I'm going to swap these together. So time would be final velocity take away initial velocity over acceleration is equal to this. Okay, so final velocity I already know is 24. Take away, and this will give me an answer 5.5 seconds. 5.5 seconds. Okay, so this is one of the equations which we need because we have a change of velocity. Okay, we've got the change of velocity going on in this case. Okay, so you can also use one of the other Svet equation if you want to. So this is one of the Svet equation that we have. You can also use another Svet equation which you want to as well for s equal to ut plus half 80 squared, because we know a already. Okay, you already, you don't know t, you're looking for t, so if you want to do this, one. Okay, right, now let's take a look what we got here. Momentum question again. Okay, now hit the floor, blah blah blah. So momentum this before it hit the floor is this much. The time it takes is this much. Work out the force. So this is the equation given to you on the board as well. So we know the equation given to you was F is equal to initial momentum take away final momentum over t. So this here is a change momentum over t, and we're looking for the force. Now the momentum before it hit the momentum before it just hit it is 0.8. So 8.7 divided by the time, and this will give us 25 Newton. This will be 25 Newton. Okay. Now this one here, to help us answer this question, this is Newton's second law. Okay, so what we have is we have the box, which is exerting a force of 25 Newton down. So therefore, the floor here, will also exert a force of 25 Newton upwards. Okay, so the force will be equal. So we know that Newton's second law is be equal. Okay, plus opposite. Okay, so the magnitude of the force is the size. The size of the force is also 25 Newton. The direction, in this case, the floor will be acting upwards. The floor will be pushing upwards. Okay, so for this one, you need to know Newton's third law. For every action, there's an equal opposite reaction. Okay, so we have the box, which is exerting a force on the floor. Therefore, the floor will also exert a force on the box. That's how it all come up. Now, this is not a question we did before, actually. There was a question like this similar one we did do now. Okay, let's take a look how can we do this. Alright, now we know the momentum, of course, so P. Alright, so we know how far it is. We know the gravity is this one. We need to look at the mass. Now, first of all, I'm going to use this equation here. Okay, because you'll see where I'm going first. So we're going to use the equation because I know at the start, so it's being held by the clamp. So here, held by the clamp. So we know that U at this point is 0. So I'm going to look for V. 0 plus 2 times 10 times this. So therefore, V is equal to okay. So therefore, looking for V. Square root this. Okay, so this is the velocity at this point. Okay, now that I have the velocity at this point, I can work out the momentum, because remember the momentum here says me the momentum is at s. So momentum at this point is 0.4. So therefore, to work out to use a momentum equation, for me to be able to use P is equal to mv, I need to know V when it is at S as well. So that's what I just looked at for. That's why I work out V. Okay, now I need to rearrange this to get M. Let's go to P over V, P 0.4 over M. Now this is going to give me an answer of 0.046. And this is the mass of the ball. It's kilogram. Okay, so this is what you need to do. Now, first of all, you can remember the equation for momentum is P is equal to mv. Now you need to ask yourself which velocity to use. You read the question tells us that momentum is at s, so therefore I need to work out the velocity at s. So how can I work out the velocity of s? So this is how I can work this out. Okay, for 4 marks. Alright, now this is also one of the questions we did before, when we did momentum, Newton's second law combined. Okay. Alright, let's take a look at this one here. Now, Newton's third law applies due to collision in this particular case. Okay. Now this guy is exerting a force, so-called is F rocket, on the rock, and the rock will be exerting force backwards, F rock. Okay, so these forces are equal and opposite. There we go. The force exerted by, okay, so by the rocket on, so this is Fr, and is equal to by F R. Okay, both of them are rocket. Let me just change this one here. FT rocket, asteroid rocket asteroid. Oh, sorry, I can just leave this out. So rocket FA rocket. Here we go. Yeah. Now state the momentum. Okay. Now first of all, I'll start with what do we know? So with Newton's second law. Okay, Newton's second law. What does Newton's second law tell us? Newton's second law tells us that the force is proportional to the change of momentum. Okay, so force proportional to change in momentum. So F is equal to this there. If you want to do this, there we go. Alright, now the law of momentum, what does it tell us? It tells us that total momentum before is equal to total momentum after a collision. Okay, given no external forces acts on the system. Yeah. Okay, it means that the total momentum before and the total momentum after must be equal, isn't it? Alright. Alright, so we know this one is true. Now if we go back to Newton's second law, that we know that momentum, so the momentum here, so this is the rocket, therefore we're going to have the same equation for the asteroid. Okay, now the change of momentum will be the same for both of them. Okay, the change of momentum will be the same both of them. So therefore we can say Fr is equal to T, Fa is equal to. So these are the same, so momentum is the same, so therefore we have the T cancel out. Okay, so therefore I have this one. Now, the last thing I would add is due to Newton's third law. Okay, so due to Newton's third law is we have opposite reaction and so on, equal and opposite reactions, so we're going to have a reaction has and equal plus opposite reaction. So therefore this would be minus this. Okay, so the forces acting will be equal and opposite. So the forces will be equal but opposite in this particular case. Okay, so that's how we can show that the forces will be the same. Okay, so if I go back to the question says explain how this statement links to the conservation law of momentum. So conservation law of momentum in this collision. Okay, so here I'm going to add time the same during collision. Okay, so this is enough for me to get 3 marks. So therefore, I plug this back in. So therefore, I have okay, so last what I'll do is I'll add this back into the momentum equation. Okay, so I add this back into this momentum equation here. So we have this, so therefore we have T. Okay. Okay, so I did something I need to change, so this is the what I need to change. Okay. So the total momentum before and after. So the total momentum before and after. Okay, so looking for the total momentum before and after the collision, of course, need to be 0. Alright, so therefore this will go to plus. So therefore this had this equal to 0. So therefore we just talk about this there itself. Okay. Alright, this is the one of the things that which we forgot to add, which I forgot to add in my explanation here. Okay, but I need to see that you've talked about Newton's first law. I need to see that you mention the law of momentum or conservation law of momentum, and any attempt of talking about Newton's third law. Okay, so what we've done here, just a quick summary. We started with Newton's second law. So we state that for Fr, which is for the rocket, this is change momentum over t, and for the asteroid, it's change momentum over t as well. So this is the equation we start with. The force is directly proportional to change momentum, and then we talk about what is the low momentum. The low momentum says the total momentum before and must be equal to the total momentum after. Okay, and okay. All right. And then, so in this case, what we have is we have the total. So try to work out the total momentum before, okay, and this should equal to the total momentum after as well. Okay, if the total momentum before is 0, so if it is 0 at the start, then we should have this here plus this here. So this is change momentum. So if you rearrange this equation here, okay, so that's where Ft is coming from. So the momentum before, the change momentum before and after is 0, so therefore we have the force of the rocket plus the force of the asteroid should be equal to 0. Okay, now since Newton's third law, we know that they are equal and opposite, so I've written down here they are equal and opposite. I'll just plug this back in, and then you see that they are equal to 0 indeed. Okay, now let's move on to the easy question. So here we're looking for the resultant force. So when the force is going to be, so which one is bigger? So this one's bigger. So the plane will be moving upwards. So therefore this will be upwards. Now how much up, by how much upwards? Therefore this take away this will give me the answer of, so this is how much upwards it's going to go. So size again, we're looking at the magnitude, Okay. Always look at the arrow. The arrow tells you which one bigger. So the bigger one, it will tend to move in the bigger direction. So therefore, it is upwards, and then you just need to minus it to work out which the resultant force is going to, because it's going to go up by this much. Okay, now this one is something we spent time doing it. So remember vector diagrams. The diagrams. Okay, there are two methods. You've got the scale method. Again, and then you got the triangle method. Triangle method or joining the thing. Okay, so here we need to construct one. Just one mark. So what I'm going to do is I'm going to draw a parallelogram. Okay, use your ruler. So this line here, and this line here need to be parallel. Okay, and then we're going to draw a dotted line here. Use your ruler again. Okay, so this line here and this line here need to be parallel, of course. So therefore, the resultant force would be in this direction. This shows which way it's going to move. Okay, now I don't have a ruler because I'm doing this on the computer, so you guys should be using a ruler. So this is my direction. So here is my resultant. It's going to move in this direction. Okay, this, because look at the plane. The plane is being pulled this way. It's being pulled this way. The only logical way, the only logical path for it to go would be diagonally to the south. That is the only logical way for it to go. Okay, because being pulled to the left, pulled to the right, and being pulled down. So where it's going to go? So the only way for it to go is diagonally down. Okay, again, try to use logic whenever you deal with these questions. Okay, it's just one marker. Now this one, gravitational potential energy, so it is stand for GPE. One of the equations you need to remember, MGH. M we know is this. G on Earth is 10. Gravity, so that's gravity. And this is the value. All you have to do is just multiply them together. They are giving you away 3 marks. Okay. And that's the answer. They're giving away 3 marks actually. There we go, done. Right, so this is a nice question here. Forces motion. So this is force motion question. So Newton's second law, Newton's third law questions. And there. Okay, now let's take a look. What we have is we have this here is bigger compared to this one. So therefore we are going to have a resultant force in this kind of direction. So resultant force here. So it's going to move up in this direction. So if we have resultant force, it means it's going to have an acceleration. So remember F is equal to ma. So F here is the resultant force. So this F here is a resultant force ma. So therefore we're going to have acceleration. Okay. Acceleration means speeds up. So the only possible way is A, speed up. It is not slowing down. Constant speed, no. Constant velocity, no. Because we have a resultant force. So let me just write this properly. Because we have a resultant force. And resultant force is equal to F is equal to ma. And we have acceleration. Acceleration is speeds up. Okay, one easy mark here. Alright, so what we have here, we have the propeller pushing the water back. Y is the thrust forward direction. Okay, so this is Newton's third law. Now let's draw this again. So we have a nice propeller. Okay, the propeller is turning and it's pushing the water here. Okay, so what you have is you have the propeller, the PFP, the propeller, pushing the water away. So therefore you can have all this water here pushed away, and those water will also be pushing back. So you can have the F water also pushing back in this particular case because of Newton's second law. That's how you go forward, because the propeller is pushing back, and due to Newton's third law, you got something else going on as well. So first of all, you're going to say the third law, okay? So propeller forces water away. So the water pushes back on the propeller. Okay. So this force. Okay, so these forces are equal and opposite. You get 1 mach for here and 1 mach for here. Okay, because that's what's happening. The propeller is pushing the water, yeah, and the water is pushing back on the propeller. And due to Newton's second law, these forces are equal and opposite. Okay, now you come to a stop, put it into reverse, runs the reverse direction, produces a force to decelerate. Okay, it takes many minutes to come to a rest. Okay, Newton's second law. Alright, so let's start with Newton's second law here. The Newton's second law. What do we know from Newton's second law? So we know Newton's second law is F is equal to V over T. So this here is change momentum over T. Okay. So this is Newton's second law. So this here is force is directly proportional, so directly proportional to change in momentum. So what's happening is going, and it comes to still for reverses. So it's going, so we've got submarine, it's going, I need to come to stop, and I need to reverse. And it says here it takes many times to do this. Okay. Right, so what must happen? So if we know it's taking long time, okay, the force on the engine is the same, okay. Alright, so it takes, here we go. So if we do F times T, it's going to change momentum, okay. Since time is bigger, it means that the change momentum needs to be bigger, okay, because in this case we're not producing a force, yeah, so we're not increasing the force or doing anything, we're just increasing the time. So how can this be affected? So the change momentum has to be affected, because it has to, the mass does not change. In this case it is indeed bigger, yeah, but I'm thinking the velocity is going to be affected. Okay, so here we go. As change of momentum is larger, okay, time is needed, so T goes up. So get 1 mark for mentioning Newton's second law, and last mark to talk about the statement that the fact that the change momentum is larger. Okay, now if we do finish this, I would like you guys to move on to some feedback questions and then some revision questions. Let's go back, just double check everything. This is a good one. Everything else should be, so this one you need to think about this a little bit more details.